Good morning to all of you. Today we will discuss a new topic in the digital signal processing, that is cascading sampling rate converters. So cascading sampling rate converters means we know what is a sampling rate converter. So sampling rate converter means converting from one sampling value to another sampling value, or one sampling rate to another sampling rate. And we have seen the applications of these sampling rate converters also. Now we will see what is the need of this cascading of sampling rate converters. Cascading means output of one sampling rate converter is connected as the input for the other sampling rate converter. Okay, then we call it as a sampling rate, cascading sampling rate converters. Simply cascading means connecting the output of one system as an input for the next system. Okay, like that you can connect any number of these systems. Here we will take up two systems in cascade. That is, first one, x of n is a sequence. Okay. So before that we will see what is the need for this. Suppose CD compact disk. This compact disk stores the data, or otherwise you can retrieve the data with a sampling rate of 44.1 kHz. Whereas a digital audio tape, this is mostly used for recording purpose. Digital audio tape works at a 48 kHz sampling frequency. Suppose if you want to transfer that data from CD to the digital audio tape, we need a sampling rate converter which converts from 44.1 kHz to 48 kHz. Okay. So therefore the required sampling rate conversion factor is a fractional value, that is 48 divided by 44.1 kHz. So this is the digital audio tape required sampling rate. This is the sampling rate of the previous source. CD, we have to transfer the data from CD to the digital audio tape. So therefore this is the required sampling rate conversion, and this is available sampling rate to 44.1 kHz, and this is the 48 kHz, which means we need a sampling rate conversion factor as 48 by 44.1. Okay, there are many applications are there. Okay, we need different sampling rates at different parts of the system. Okay, that is why cascading the sampling rate converters is a very useful in the real time signal processing. Okay, that is why what we have to learn it. Okay, what is how to cascade two systems or three systems, like that we will see. Four systems like that, so we will see that. So therefore, sampling rate conversion, cascading sampling rate conversion means connecting the interpolator and decimator. The output of interpolator is given as the input for the decimator, like that. So sampling rate conversion means converting from one sampling rate to another sampling rate. In real time applications, we have seen if you want to transfer the data from CD to digital audio tape, CD operates at this sampling frequency, digital audio tape works at this 48 kHz. So if you want to convert that from one sampling frequency to another sampling frequency, we need a sampling rate converters. Okay, so now x of n is the input sequence. This x of n is represented by some number f, letter f. Now this initially x of n is upsampled by L. After that you have a anti-imaging filter. So the purpose of this anti-imaging filter is to remove the images. And decimator, after that we have a decimation by M. So before going to the decimation, we have a HD of Z. Okay, this HD of Z is an anti-aliasing filter. So whenever aliasing takes place, aliasing means overlapping of the adjacent spectral components. If that overlap takes place, you cannot recover the original signal. Okay, whenever that takes place, you cannot recover the original signal. So that is why before the decimator only we are so removing that any high frequency components are present, those are removed by anti-aliasing filter. After that, this interpolated signal is decimated by M. So therefore output you will get as y of n is, so L multiplied by F by M, or L by M into F. Okay, that is how now we see this L by M can be anything. It can be, see, 2 by 3 or any other factor like this. You also can have a different stages. Okay, so therefore L by M into F is the output. Now you see the original input sequence x of n or F is down, or otherwise this is converted by L by M. Okay, original F is so modified by L by M, the factor L by M. Now this block is called totally with interpolator and filter. It is called interpolator, and decimator means it is a anti-aliasing filter again. So we have a decimator. Those two are called so decimator. Now, so see this HU of Z, which means anti-imaging filter, HD of Z anti-aliasing filter, both works at the same sampling rate. So that is why in implementation we can replace these two by a single low pass filter. Okay, single low pass filter of transfer function H of Z, and operating at the same sampling rate as that of the HU of Z and HD of Z. Okay, now these two blocks are so replaced by a single block H of Z. Now see, this is also same, right? X of n, the original sequence X of n upsampled by L, then it is passed through a low pass filter of transfer function H of Z, then it is downsampled or decimated by M. So then output is FL by M. Okay, so therefore, so what is the sampling cascading sampling rate converters means? When an interpolator and decimator, if you connect L interpolator followed by M decimator, then we say that it is a cascading of sampling rate converters. Okay, so this is another one sampling rate converter. This is another sampling rate converter. So this sampling rate converter converts the input sequence X of n by L, or upsampled by L, and that is downsampled by M. So therefore when you combine this, what you will get is, we get a cascading connection. Output of this low pass means upsampler is connected as input for this downsampler. This is the one cascading connection. So L interpolator followed by M decimator. Okay, this connection is called cascading of sampling rate converters. Okay, so very simple. It is a very simple. So L interpolators followed by M decimators is called cascading sampling rate converters. And what is the purpose of this? To convert one sampling rate to another sampling rate. So example is, from if you want to transfer the data from compact disc to digital audio tape, we need a sampling rate of 48 by 44.1. Okay, to get that factor, so we have two such type of operations. Okay, to understand in some more detail, we'll discuss one problem, how this works, and what is the meaning of what is the meaning of this L, how it is down converted. You will see that. We will see with an example. So therefore, we'll go for the, there is this. We'll go for the next. Consider now. See, we will see one problem that is related to this cascading of sampling rate converters. Consider a sequence. Sequence means input sequence. X of n. X of n is equal to 1, 3, 2, 5, 1, -2, +2, after that 3, 2, 1. Okay, this is the sequence. This is the given sequence. Now what we do is, first what is the cascading sampling rate converters? So first we have a L interpolators. After that, so we will have a M decimators. If you connect these two, output of interpolator as the input for the decimator, then so we say that it is a converting cascading sampling rate converters. Okay, now we will take L is equal to 2. Okay, L is equal to 2, which means upsampling. Okay, upsampling by a factor 2. Okay, upsampling by a factor 2. Okay, now when you upsample it, so what you will get is, so upsampling means what? So L minus 1 zeros, L minus 1 zeros are inserted between two adjacent samples. Two adjacent samples. Okay, L minus 1. Now L is 2 here, so therefore L minus 1 is equal to, that is 2 minus 1, which is equal to 1. 2 minus 1 is 1, which means the meaning of this is we have to insert 1 0 between every two adjacent samples of the original x of n. Okay, original x of n. Now that x u of n is equal to x of 2n. Okay, x u of n is equal to x of 2n. So x of 2n means u for upsampling or interpolation. So this u for upsampling or interpolation. So therefore x of 2n means, so what is the meaning of this? So L minus 1 zeros are inserted between two adjacent samples. So therefore first we take 1, okay, 1. After that, so how many zeros we have to insert? 1 0. So 0. After that 3, again 1 0, 2 0, 5 0, minus 1 0, minus 2 0, 2 0, 3 0, 2 0, 1, right? This is what happens. After that you don't have any samples. Like this. So now you observe, you can clearly observe that. So initially, so how many samples you have? See, 1 2 3 4 5 6 7 8 9 10 samples are there. Now the samples are doubled because we have a this L minus 1 zeros are inserted between two adjacent samples. Okay, this is a upsample sequence. Okay, this is the original sequence. This is the upsample sequence. And what is upsampling? So value means, so L is equal to 2. L is equal to 2 means we have to insert 1 0 between two adjacent samples. L is equal to 3 means we have to insert two adjacent samples between we have to insert zeros, 2 zeros between two adjacent samples. Now after this, what we do is we do downsampling by a factor m is equal to 3. By a factor m is equal to 3. So m is equal to 3 means it is downsampling by a factor 3. Downsampling by a factor 3. Now that is represented like this: x d of n, that is d for downsampling. This is x like this 3n. So the meaning of this is now okay, now we will see the downsampling by a factor 3. Okay, now downsampling means already you have this upsampled signal. This upsampled signal is downsampled by 3. Now that is the final output. Final output yn is equal to. So downsampled means, what is the meaning of downsampling? So we discard m minus 1 samples. Okay, discard m minus 1 samples. That is the meaning of downsampling. So therefore m minus 1 sampling means m is equal to 3 here. M minus 1 samples means 3 minus 1, 2 samples we have to discard. Okay, so that final output y of n is equal to, first you take first sample, after that so you discard these 2 samples. Okay, then 0 you taken this, after that you discard these 2, then 5, after 5 you discard these 2 samples, 0, this 0, and after that you discard these 2 samples, then 2, then after that you discard these 2 samples, then 0. Okay, then you take this 2, then discard the remaining 2 samples. See this? So initially we took the first sample, then discarded these 2, then that's why you get 1 here. After that, so you take this 0, then you discard these 2 samples, then you take 5, then discard these 2 samples, then you take 0, you discard these 2 samples, after that you take 2, you discard those 2 samples, after that you take 0, you discard these 2 samples, then you take see, so initially, so 1 is taken and 0, 3 are discarded, then 5 you get it, so 1, after that 0, 3 are discarded, 0 you will get, after that 2, 0 is discarded, 5 is taken, then 0, 1 is discarded, 0 is taken, after that minus 2 and 0 is discarded, 2 is taken, after that 0, 3 is discarded, 0 is taken, after that 2, 0 is discarded, that's why 1, if you take 1. Okay, now this is the output sequence. Now what you have done, see, first if you represent it diagrammatically, first what we have done is the given sequence x of n, this is x of n, this x of n is upsampled by 2, okay, factor 2. Okay, after that so this upsampled signal is downsampled by a factor of 3, so you get some y1n version, that y1n. Now what to do is, so we have to do in the reverse way. See, so now we got a 1 0 5 0 2 0 1, okay, for the entire samples. Now what we have to do in a reverse way, which means first what to do is, so you have to take this L is equal to, first we downsample the sequence by 3, then we upsample the sequence by 2. Okay, that in that case also we have to get the same answer. Okay, we have to get the same answer. Now we will see that. Okay, here the idea is, can you replace these two? Means first you can take downsample, then you take upsample. Now this is assume that it is a y1n. Now the same thing we'll do in the reverse way. Now what to do is, first you downsample the sequence by 3, then you upsample the sequence by 2, a factor 2. You assume that this is a y2n. Previous one is y1n and this is y2n. Now, so x of n is there. Previously what we have done, initially we upsample the sequence by a factor 2. After that we have downsampled by 3. Okay, now we have to do in the reverse way. So therefore, first we will see this upsampled signal, downsampled signal by 3. So therefore, xd of n is, here you will get xd of n. Okay, xd of n. So xd of n means what? So here m value is 3. M value is 3 means we have to discard m minus 1 samples. We have to discard m minus 1 samples. Okay, discard m minus 1 samples, which means m minus 1 is 3 minus 1, 2 samples. We have to discard the 2 samples of this original sequence. Okay, now see, first initially you take 1, after that you discard 2 samples, then 5, after that you discard these 2, then you take 2, after that you discard this 2, then you will get 1. Okay, so this is a very clear, right? So discard m minus 1 samples between 2 adjacent samples. Means so first you take the first sample, then you discard m minus 1 means 2. You discard 2 samples, 3 and 2 are discarded. 5 is taken. After that 2 samples are discarded. So plus 2 is taken. After that 2 samples are discarded. 1 is taken. Total 4 samples you get it, right? So 1, 5, 2, 1. This 1, 5, 2 and 1. Okay. Now what we do is, after this, what we have a upsampler by 2. The upsampling factor or interpolating factor by 2. So now see, so y2n will get y2n, final output y2n. So here, so upsampling factor is 2. What is the meaning of upsampling? Upsampling means, so insert L minus 1 zeros between 2 adjacent samples. 2 adjacent L minus 1 zeros between 2 adjacent samples. Now you see, what is L? L is 2 here in this case. L is 2. You see, this is the interpolating factor. L is 2. So L minus 1. L minus 1 is 2 minus 1 is equal to 1. 1 0 we have to insert between the 2 adjacent samples. So therefore y2n is equal to, first you take the first sample, then how many zeros you have to insert? 1 0, then 5, 1 0, 2 0, 1 0. See, just between every 2 adjacent samples we are inserting a 0. See, here 1 is there, after that 0 is inserted, then 5 is taken, after that 0 is inserted, 2 is taken, like that. So 0 1 0. This is the output sequence. So now in the previous case also, whatever we have seen means upsampler followed by downsampler, and downsampler followed by upsampler. In both the cases you will get the same answer. So therefore y1n is equal to y2n. y1n is equal to y2n. Okay, this is what to understand. You can interchange decimator and interpolator. In the previous case, first we have a interpolator, after that decimator. Now we have a decimator, after that interpolator is there. Okay, that in both the cases you get the same answer. Okay, y1n is equal to y2n. But so every decimator and every interpolator you cannot replace or interchange, and we have a different, there is some condition is there on this to interchange the decimator and interpolator. So that is why, so whenever, see, we can take one other example, and using that example you check it whether it is same principle or same result is valid or not. You can check it. Suppose you can check it for like this one. First you take 2 and 4. Okay, as a next example, as a homework, you take it as same sequence for the same x of n. You take first you interpolate it. L is equal to 2, m is equal to 4. Okay, and now you interchange these two. First you upsample the signal by 2 and downsample the signal by 4. That you take it as a y of y1n. The output is y1n. Okay, output y1n. Then in the next case you take, first you do the downsampling, and after that L is equal to upsampling. In this case you get y2n. You identify whether y1n is equal to y2n or y1n not equal to y2n. Okay, you find out these two and you tell me whether they are equal or unequal. So even try to find out the reason if they are equal or unequal. So what is the answer, you try to find out. Then we will meet in the next class. Thank you, and you solve this problem. If you have any questions, we will see it in the next class. Thank you.